So last time we talked about covariance matrices, the properties of covariance matrices, and in particular this interesting identity for how the covariance matrix undergoes transformation if you apply a linear transform to your random vector. We talked about the fact that covariance matrix is a quasi-semi-definite, and we also briefly mentioned the correlation. So I'm just going to be brief. You can read this for yourself, and we may come back to it later. And the point is that I want to have a linear transformation. So if I have a random variable y, I want to see if I can find a matrix A such that then I transform y by this matrix. So remember, matrices are linear transformations. I get a new random variable. Let's say of the same dimension. So this is n by 1. This is n by 1. This is n by n. So can I choose A such that can we choose A such that I get covariance of z is equal to identity. I put an n here usually to indicate the dimension of the identity. So the identity matrix is the matrix whose elements are, it's a diagonal matrix, diagonal elements are 1, off-diagonal elements are 0. And so this is nice when we have something like that, because it is like the standardization of a single random variable. So if you have a single random variable, sometimes you normalize it by dividing by the standard deviation so that it has variance 1. So doing this procedure, z has all the variances of the components equal to 1, and the components are uncorrelated. So this is why we call it decorrelation or whitening. So this is sometimes called the white noise. It's nice because the variables are like z is related to y by a linear transformation, and so it retains the higher order dependence structure, but the correlation is gone. So you might want to use this transformation as a pre-processing in analysis. The question is whether there is such a, and the answer is yes. There are actually multiple, but one version is sigma negative 1/2. So if you remember what sigma 1/2 was, anyone remembers? This is just the inverse, yeah.
Sigma 1/2 was the square root of the variance. Basically, you took the square root and multiplied by itself.
Great, yeah. So sigma 1/2 is the square root. If you multiply sigma 1/2 by sigma 1/2, you get sigma. Sigma here is the covariance matrix of y. So sigma minus 1/2 is just, you can think of it as sigma 1/2 inverse. Okay, assuming that the covariance matrix is invertible, the square root is going to be invertible. And so this is also equal to like sigma inverse 1/2. So that's why it doesn't matter how you write it. You write it negative 1/2. You can invert the matrix and take the square root. So as an exercise, I've done it here, but this is an exercise in using that formula. So covariance of z is going to be A, covariance of y, A transpose. You plug in this particular A and you will see that it works. So it turns out to be the identity. So I'll leave the details to you. How do we calculate the sigma inverse? A simple way of doing it is, if you remember, did we talk about how to calculate sigma inverse? Like, sorry, sigma 1 negative 1/2? No, okay. So if you do the eigendecomposition of sigma, then it's easy to show that the symmetric square root is going to be u lambda 1/2 u transpose. So if you have, this is the eigendecomposition, EDD, eigenvalue decomposition, lambda is in the diagonal matrix. You just apply 1/2 to this, and this works. Similarly, sigma inverse is going to be u lambda minus 1/2 u transpose. So you just apply the transformation to the middle guy. And it's clear what the square root of a diagonal matrix is. You just take the square root of the diagonal elements. This one also clear. So you just invert the diagonal elements. So the diagonal matrix is everything is simple. And also similarly, sigma minus 1/2, combination of these two operations is you apply minus 1/2 to the middle guy. So this one These two you can verify. So how can I verify and multiply this by itself? It should give me sigma. Do that as an exercise and use the property that you use with orthogonal. This one I multiply by sigma, I get identity. This you can also verify. This one follows from the same set of principles. So you can multiply this by itself, you get sigma inverse, you get like this. Or you invert it, you get like that. So verify as an exercise. Okay. So eigenvalue decomposition give you a way of doing this rather easily. Okay, taking the square root of a matrix or the inverse of a matrix, if you have the eigen decomposition, is very simple. At least a symmetric matrix. Good. Okay, we'll may come back to this, but I just wanted to point out as a note. Questions? Okay, so now I want to talk about multivariate normal distribution. And the this is like a multivariate extension of the usual normal distribution or Gaussian distribution. What is the univariate normal distribution? Yeah.
The univariate normal distribution just takes that bell curve.
So what is that bell curve?
It has very short tails and it like peaks.
Right, but what is like the relation of that curve to the random variable?
The distribution?
Distribution, it's the PDF, right? So X is, let's say, normal, it means 0 and 1. If the PDF looks like this, so let's write it as P f of X of X. It has this shape. So the bell shape, 0 is going to be maximum, goes like that. So the tails are going to 0 very fast. Okay. E to the negative x squared is fast. It's symmetric, so I can. So what does the PDF mean? Just to recall. So technically, PDF is not the distribution, if you remember, I mentioned that. But it's enough to get you the distribution. So anyone remembers what the distribution really is? Probably not. So distribution is usually, like if you want to be technical, is this set function. So it maps A to the probability of X in A. So for every A, reasonable A, event A, I should be able to assign the probability that X lies in A. So this is really the distribution, it's a set function. So how do we calculate this? Why did I say, for example, that it's enough to have the PDF to get the distribution? Can I compute that based on the based on the PDF? Yeah.
Not for continuous anything. Because otherwise it won't add up to 1.
I can calculate the probability that X is in an event. So if I have a Gaussian, can you calculate, for example?
You can do an integral, but not like a specific thing.
Okay, let's do the integral. So how do you write this?
It's the integral from 1 to.
Okay, I write it as this, minus 1 and 2. So if you integrate the PDF over that set, you get the probability. So the X. Okay, so you integrate this over any set. It gives you, if this is the set A, you integrate it, it's just a mass that's on top of this. It gives you the probability. So PDF is something whose integral over any set gives you the probability that X is in that set. Okay. So what is now a multivariate distribution? Or like multivariate Gaussian distribution? So multivariate normal distribution is a distribution we can specify it by the PDF again. So technically, it's again a set function. So if I have a random vector, x is to xn. Right, so this is the standard normal. There's a standard sort of or canonical normal distribution for a Gaussian vector. So what would it be? Like if you specify the PDF, you're done. You want to remember it's the so suppose the entries are independent, right? So suppose xi's are IID, normal 0, 1. Then you write down the PDF. Fx, x1 up to xn. What happens to the PDF if you have, so when you say the PDF of a random vector, it's just a multivariate function. It specifies like how the density, like the probability is distributed, the density of the probability over the entire n-dimensional space. So can you write down a formula for this? Yes.
Product.
Great. Yeah. So this would be f, let's say xi of xi. And so these are going to be what? 1 over root 2 pi e to the negative xi squared over 2. Right? So how would it look like when I expand it? So this would be 1 over 2 pi n over 2, right? E to the negative summation xi squared over 2. So you get 1 over 2 pi n over 2 e to the negative norm of x squared over 2. So that's the PDF of this vector x. Okay, so it's proportional to the e to the negative of x squared. So as the norm goes like, so the norm, the level sets of this are where the norm is constant. So if you look at the norm, for example, x squared is c, the location in R2, let's say things are in R2, would be like a circle. So in these circles, it will have the same problem, like the same density. So here you have a lot more mass. And as you go around, the mass starts to drop. So here it peaks and then it goes down. It's like a bell-shaped, circular, symmetric function. So I can't plot it, but imagine a lot of mass here. And as you go away, the mass goes down very quickly. But it's the same amount of mass sort of around each segment. Okay. If I want to move it, like have a mean, I just move the entire thing. So if I want to have, this is centered at 0. If I want to center it at some other point, I would have, so this one, if you write down, this would have normal, which means 0 and covariance matrix identity. Okay, because their IID, the variances are 0, so the variances are 1. So the covariance matrix, so when you write down a normal multivariate normal distribution, you specify the mean here. The mean is going to be 0 because you know the mean of every coordinate is 0. And the covariance matrix is going to be identity because the elements on the diagonal are 1, the variances are 1, and because of the fact that they're IID, entries are IID, the off-diagonal elements are going to be 0. Things are going to be uncorrelated. So that's that. If I want to go from this to, so this is the PDF of this. So if I want to go to, let's say normal, which means mu, and identity here. So what would I do? What should I do in terms of the PDF? So when you want to do this is centered 0. If I just shift everything to mu, this would be a nice PDF for this. So I'm going to have the same thing here. I'm just going to shift it to mu. So you can, if you know a little bit of calculus, you know what happens to this function. The function is exactly the same thing, but everything is shifted to mu. So mu is going to be 0. And so everything is going to be shifted now to the location mu. So this point is going to be mu, and then I'm going to like have drops around this. So everything is like just a shift. So it's easy to introduce a non-zero mu. It's a little bit more tricky to introduce a general covariance matrix. Okay. And I want to see if people have seen that. How do you introduce a general covariance matrix? So what will be PDF if I want to write something like so we can write this from first principles, but I'm not going to do it. I just assume that you know. So this thing can be write as like x minus mu transpose x minus mu. Okay. So what happens to the density in this case is going to be f of x is I get e to the negative x minus mu transpose, but then I put a sigma inverse in between. Okay. Why you have to do this, there's a lot of good reasons for this. If you had time, I would try to drive this for you, but you don't have time. So this is going to be n over 2, and then sigma 1/2 goes in here. So this is the determinant. You can see if sigma is one identity, this would be identity, this would be identity, and we get the other one. But this is the general way of writing the PDF of the multivariate normal distribution. It's just this part is the key, sort of. This is a quadratic form, this is another quadratic form. So this is symmetric around mu. This one is not. So if you plot the level sets of this, in this case, it would look like, anyone knows what the level sets of the PDF are in general? Like, how do they look like? They look like ellipses, so ellipsoids. So it's not circularly symmetric anymore. And the directions of this would be the directions of the eigenvectors of the sigma. But you can see if you have a lot more correlation. So for example, if this is 1, this is 0.9. So they're very correlated, the coordinates. It can't be circularly symmetric because that's sort of independence. This would be very very much like this. The level sets are going to be, when I do it like this, there's a lot of mass close to this line, the 45-degree line. And so the PDF shows that as well. Okay, so in any case, this is the general formula for the PDF of multivariate normal distribution with mean vector mu and covariance sigma. Okay, so it's a distribution for an entire random vector. But the PDF is just applied to y, it's just give you a scalar. So it's just the density at that particular point of space. So if I want to use this, I have to integrate it over a certain subset of the space. So for example, from R2, I want to figure out what the probability is that this random variable lies in this set, I have to integrate the density over the set, gives me the probability that this random vector is going to lie there. I have 3 coordinates, so and in general, I'm going to integrate. So the probability that y is in A is going to be integral over the set A of Fy Ey. So these are multivariate integrals. Okay. So the P, yeah. Talking about this?
Yeah.
Yes, that's the square root of the determinant. So sigma 1/2 is root. This, you can also write it as root det sigma. This is another notation. So we can actually derive this density if you define the Multivariate normal distribution in a different way. If you want to define it, you can start from this definition. You can say a multivariate normal distribution is a continuous distribution in Rn that has this general PDF. This you can use as the PDF as the starting point definition, which we do here. In like other courses, you can start from like a more natural definition and derive this formula actually. We derived a little bit of it. You can see like it matches, at least it matches the case where, for this case, that things are IID normal 0, 1. You can also extend this. So if this was sigma I, for example, you can still do this. So you can write down the PDF and it's consistent with what you get here. So in the case where the coordinates are independent, if the coordinates are independent, you know the individual marginals and you can construct a joint from individual marginals and you should get a consistent formula. And this is going to be consistent with that. So we can't just come up with anything that we want. At least it has to satisfy this property that whenever the coordinates are independent, I get a PDF which is valid according to this like product rule. And it turns out that it is. So we did a little bit of that here there. So this is multivariate normal distribution. We write it like this: mu sigma. I might put an n here if I want to emphasize the dimension, and so on. So there is an implicit assumption that sigma is invertible. Sigma is non-invertible. You'd have a degenerate Gaussian, or something called Gaussian, multivariate normal or Gaussian. It's going to be degenerate distribution. We're not going to go there. We talked about what happens if the sigma is non-invertible last time, if you remember. The distribution would be restricted to a subspace, and it wouldn't have a density, proper density. Questions? So this formula is useful to understand the shape of the density to calculate these probabilities, but in this course, we're not going to use it much. Instead, we're going to develop, it's like similar to the expectation and the covariance, things like that. There is an integral formula if you have a continuous distribution, but we developed a calculus to deal with linear operations. And if you have a nice calculus, you don't have to calculate integral. So you can calculate the expectations of covariances of linear transformation of random vectors without doing any integration. This is the same. So the main property, or the most important property of multivariate normal distribution is that it is closed under affine transformation. So you would, if I do an affine transformation of a random vector whose distribution is multivariate normal, I would get another multivariate normally distributed random variable. So suppose y is normal with mean mu and variance or covariance sigma. Affine transformation is something like that: a times y plus b. If b was not there, if b was 0, you would call it a linear transformation. Mathematically, they call it this an affine transformation, to be precise, because of that possibility of that extra b there. It doesn't satisfy the conditions of linear transformation. So if I add y to y prime, the transform of y is not going to be. So if you have a linear transformation, you have something like that. This is not going to be satisfied if I have a d there. If I don't have a d there, it's going to be satisfied. So that's why it's sometimes called affine. In any case, so if you have an affine transformation, the main property which you don't prove, and in some courses you can take this as the definition of a multivariate normal distribution, is that this U is going to have a multivariate normal distribution. Okay, so affine transformations does not move you outside the family of these distributions. So U will have a normal distribution with mean mu tilde and covariance sigma tilde. Mu tilde would be, so now we can calculate. I'm going to tell you that the distribution is like this. A normal distribution is specified by the mean and the covariance matrix. So I just have to be able to calculate the mean and covariance matrix. And we already know how to calculate it. So the mean here is going to be the expectation of, let me do that. So let's calculate the mean. So can anyone calculate the mean for this? Expectation of, by definition, this is AY plus B. Yeah. Sorry?
A mu plus B.
Okay.
A just shifts it over and then multiply towards the sigma.
Yeah, so this is linearity of expectation, if you remember. And so you get A mu plus B. Okay. So how about sigma tilde? This is the covariance matrix of U, covariance of A y plus B. So like this.
So specific covariance of AY equals A times covariance of Y times A.
And this is just A sigma A transpose. So why is the first step true?
Because the constant shape doesn't change the shape of the distribution. So it's not gonna influence.
Yeah, in general, constant shift is gonna change the shape of. So it's gonna change the mean, but not the covariance, for example. Okay, so you can say this. Okay, yeah, shift invariance of covariance, or the shape of the distribution, if you want to say. And the second one is the formula that we developed. Okay. So this part we already know how to do. There's exactly the same things that we derived. So the only bit of information that I'm adding is that the whole distribution is going to be multivariate normal. Okay, if this transformation happens to a random variable, the mean and the covariance are always going to be transformed like this. Okay, so these two formulas for the mean vector and the covariance matrix are always true, as we have seen. But the distribution might be something else. If you're like an exotic distribution, if you do a affine transformation, the new distribution might not be from the same family, or you might not be able to recognize it. But in the case of the normal distribution, we are going to land in the same family. Okay, so it's not going to be a new set of distribution, a new family distribution. So you're going to have the same kind of PDF, but you just change the mu and sigma. And this is the most important property of the multivariate Gaussian distribution. Okay. It's very useful for us because we're going to do work with linear transformations, linear models. So everything will be Gaussian because we were going to deal with the Gaussian, like it's affine transformations, and they're going to stay in the Gaussian family. Questions? Yeah. Oh. Yeah, sorry. I think we might have we used to have a battery, it's just now 0. Unless you have like spare batteries. You don't know why it suddenly drops. Okay, so it's gonna go up. Maybe like 1 more minute of this. But, marginal distributions. Okay, so this is the first statement. And a special case of this, if I have A transpose Y, where A is a vector, so this is going to be a scalar. The special case is that any scalar, this is going to be basically a linear combination of the elements of Y. And you would see that this is going to be, if you plug in the formula, it's going to be normal random variable, but because it's scalar, it's going to be just the scalar normal random variable with this mean and this variance. Okay, so the variance of, so this tells you how the variance and the mean of the linear combination undergo change, and we also know that the resulting linear combination is again Gaussian. Okay. Okay, that's one approach. So, for example, if I have y is like y1, y2. Okay, y1 plus y2 is going to be Gaussian. Okay, also y1 plus y2 minus this is also, this is going to be multivariate Gaussian. And any sort of linear transformations would be Gaussian. Okay. Questions? Now, second property is marginal distributions of a multivariate Gaussian, or again, multivariate Gaussian. So a marginal distribution is the distribution of a subvector of Y. Okay, in the extreme case, the distribution of individual coordinates. So if we have a multivariate Gaussian distribution, individual coordinates are going to be Gaussian. But also, like, for example, we take y1, y2, y3. Okay, this is multivariate normal, which means mu1, mu2, mu3. Sigma 1, 1, sigma 1, 2, sigma 1, 3, sigma 2, 1, sigma 2, 2, 3, sigma 2, 3, 1, sigma 3, 2, sigma 3, 3. So let's say I want to calculate the distribution of y1, y2. So this is a particular marginal because it's a subvector of the original three-dimensional vector. So can we use the first property to calculate this? Can I write this as a linear transformation times y1, y2, y3? Yeah.
1, 0, 0. No, 1, 1, 0, sorry.
1, 1, 0.
Yeah.
That would give me y1 plus y2.
The other way? The column?
But the other side is going to be 3. So this has to be 2 by 3. So you have to give me a 2 by 3.
1, 0, 0, 0, 1, 0.
1, 0, 0, 0, 1, 0. Okay, this would work. Okay, so this is a linear transform. So marginals you can write as linear transformation. So this is a special case. 2 is a special case of 1. Okay, and when you do the multiplication, I'm not going to do the multiplication, but for example, the covariance of this is going to be, so it's going to be normal between A mu and A sigma A transpose. Because of the special nature of this, this is like the identity. So you can write it as, in this case, this is like identity 2, and then the 0 here. Okay, because of this nature that it's some sort of identity, what happens is this simplifies. And the effect is that you're going to pick this submatrix of sigma and this submatrix of mu. So that would be, this would be the covariance matrix of this, and this would be the mean of that. And this all follows from this multiplication. Okay. So marginals are Gaussian, and it's a special case of what we had before. Now, so this is doing it in a more general form, but just the same thing. So if you have an n-dimensional vector, you pick a p-dimensional subset, you would get that. So the same goes if I have like the same thing here, but let's say I want to calculate this marginal. So they don't have to be contiguous. So y1, y3. I1 distribution of y1, y3. You can still write it in the same fashion. Okay, and the result, if you go through, is going to be a Gaussian with this mean being this part of the mu, and the covariance being the submatrix of the covariance that's on these rows and columns. So I'm looking at row I and the element 1 and 3. So I'm going to look at the submatrix on rows 1 and 3. So submatrix of sigma on rows 1, 3 and columns 1, 3. So it would be normal with mean mu1, mu3, and the submatrix of sigma. Okay, now this also follows from the same argument. Okay, any submatrix, any subvector, basically. And if you do just the single, so you want to read the single, I'm not going to do this. Okay, if you want to just have a single, so what is the distribution of y2? That's also a particular marginal. You do the calculation, we did it. It would be very simple to this. It would be like a times y, where a is, so y2 would be like 1, I say 0, 1, 0 times y1, y2, y3, and you can go through the argument. This is like A transpose. And it gives you that the mean is going to be this, and the variance is going to be this. And so it's Gaussian with that mean and variance. So all the marginals are easy to calculate, and they're Gaussian. Questions? This is it. Okay, third property. Third property is that conditional distributions are Gaussian or multivariate Gaussian. This is a very interesting property, but you're not going to use it much. So I'm going to be very brief. So what I mean by conditioning, so do people know about conditioning? Conditioning one random variable on another? Yes.
You basically already know one of the.
Yeah, good. Yeah, so that's the idea. So conditioning means I know, for example, well, in this case, what we want to do, for example, I have y1, y2, y3. Assume that I actually observe y3. I know that this is coming from a multivariate normal distribution. Assume that I observe y3. Okay. This observation changes its distribution of the other two. If they're, for example, very correlated with y3, I know now more about them. So originally, they were like more random. But once I know y3, if they're independent, it's not going to change anything. So if the coordinates are independent, once I know y3, it doesn't give me any information about y2 or y1. But if they're very correlated, once I see y3, I know more. Okay. So that changes its distribution of y1, y2. So marginally, they had a particular distribution. Now conditional on y3, they have another distribution. So what I want is like y1, y2, condition on, let's say, y3. Okay. the claim is that this is also going to be a normal distribution. It's going to have a certain mean, which is going to be a two-dimensional vector, and a certain covariance matrix. This one you can prove from basically the form of the PDF. If you remember how to do it, the PDF of this is going to be, let's say y1, y2, conditional on y3, is going to be like the PDF of the joint, which is y1, y2, y3, divided by the PDF of y3. Okay, so you do this division, you simplify, and it turns out to be still multivariate normal. Maybe I'll assign it as an exercise, it will be fine to do a simple case. So from the first principle, you can do it, but if you do it in general, this is also going to be like looking like a multivariate normal PDF. And then you can read what the mean and the covariance are. And they're not that simple. But I'll let you know, for example, how to do it in general. So these are the formulas. How can I explain this? So there is a formula for mu, and there's a formula for sigma. It's non-trivial, okay? But there's some logic to it, okay? And so this formula, if you want to understand, let me do this. It's easier, okay? So I want to say y1 conditional on y2. So here, what I'm doing is like I subdivide into two pieces, okay? This is a special case of that where this is y1, this is y2. But unfortunately, the notation is unfortunate because maybe I should have written it like this, y1, y2. It's a subvector. So y1, y2. So this is going to be normal. The mean is going to be, what would be the mean? The mean is going to be in general. So you can think of the, let's see if I can explain it. So suppose the mean is not there, okay? So suppose these are zero mean. So zero mean. And then there's a covariance matrix, which I'm going to write it as sigma 1, 1, sigma 1, 2, sigma 2, 1, sigma 2, 2. So the point here is this is not the 1, 1 element. It's just the block element. So let me do it here. Let me get there. I'm going to subdivide the covariance matrix into two parts and the mean into two parts. So let's say this is zero mean. There is a block here, which is sigma 1, 1. There's a block, which is sigma 1, 2. A block, which is sigma 2, 1, and a block, which is sigma 2, 2. So in this case, for example, it would be, this would be 2 by 2. This would be 2 by 1. This would be 1 by 2. This would be 1 by 1. So depending on how this would be, for example, 2-dimensional. This would be 1-dimensional. But in general, it would be, yes.
So by division, sigma 1, 1 and sigma 2, 2 will be square, but the other one's not.
Great, yes, yes. This would be square. The same dimensions as this. This would be square, the same dimensions as this. This would be like the cross covariance, yeah.
The other two are equal, right?
The other two, these two would be transpose of each other. So sigma 1, 2 would be, or sigma 2, 1 would be, it's the same, transpose of this. The transpose. So in this particular case, it would look like a two-dimensional part and like something like this. So this would be sigma 2, 2. This would be sigma 1, 2. This would be sigma 2, 1. This would be sigma 2, 2 in the case that I have here. Okay, this is that case. But in general, it will be, if this is p dimensional, this is like d dimensional, this would be p by p, this would be d by d, and the other one would be p by d. Okay. So let's say this is p by 1. This is d by 1. This would be p by p. This would be p by d. This would be d by p. This would be d by d. So this would be d by d. This would be p by p. So okay. So these are block covariance matrices. So if you do this blocking, then what happens is that I'm gonna basically decorrelate this. It's not decorrelation, but like not decorrelation, but take the inverse of this and then you map it to 1. So 1, 2, 2, 2, 2. That's sort of the mean. That's how the mean of this works. So mu1 would be you apply the inverse of sigma 2, 2 to this and then map it back to 1 by 1, 2. So dimensions match. And the covariance would be this would be mu. Let's call this mu1, 2. It's hard to remember first. This one would be the original covariance block. This is the covariance block associated 1, 1. So this is 1, 1. So the covariance block original, but there's something subtracted from it. So when you condition, you reduce the variance. The thing that you subtract is like 1, 2, 2, 2, 2, 1 inverse. So this gets subtracted. So you can think of there's this reduction in variance. So I don't expect you to remember this, but there is a logic to it. So you have sigma 1, 1, and then you want to subtract this, you get 1, 2, 3, 2, 2, 1. And why it looks like this is there's some reasoning, but the same goes here. So 1, 2, 2, 2, 2. The main point here is this part. So you can see the mean here is not going to be constant. So really this is, I should write it as mu 1, 2 of y2. So it's a function of y2. Okay, so this goes there. So the conditional mean depends on the part that you condition on. So once I condition on y2, that's fixed. Now the distribution can depend on that. Okay, and it turns out that the mean depends on it. So the mean is just a linear transformation of that y2. Okay. Used to be 0, but now I know more. And once I observe this, I'm going to be like close to y2. I can sort of some sort of close, but this is the transformation you can apply. The covariance in general would also depend on mu2 for a general distribution, but in this case, for the Gaussian case, the covariance is constant, the initial covariance. This is very special. It doesn't happen in general. But the main point is that the distribution is changed, and in particular, the mean now depends on the condition part. Okay. And if the main point that I want to make is that if this sigma 1, 2 is 0, right? The sigma 1, 2 is 0, this is going to be 0. And this part is going to be 0. So you get that the conditional distribution of y1 given y2 has 0 mean and covariance is sigma 1, 1. So that's the marginal distribution before condition. So if sigma 1, 2 is 0, we get the same distribution as if we didn't condition. Okay, so there is no dependence of the conditional distribution on y2 anymore. And that means that the two components are independent. So this conditioning formula, the main purpose that I mention it is to observe that if sigma 1, 2 is 0, then this implies that y1 and y2 are independent. Because the conditional distribution of this given that is no longer dependent on y2. And it's going to be back, this will always be 0, it's going to be back to the marginal distribution. So the marginal distribution of y1 here is going to be normal with mean 0 and covariance sigma 1, 1. This is the marginal distribution. Conditional distribution is in general different unless sigma 1, 2 is 0, it gives you back the marginal distribution. So that's the main point that I want to make. Is that sort of clear? Clear or not? Question or This is a little bit tricky. In general, you would have the general mu. So the idea is that you subtract mu. So subtract mu2 from mu y2, and you can see I can subtract mu1 from this. So this is really for the I can put mu's here, and the general formula follows. It's a little simpler if you ignore the mu's, but the general formula you can see I have it here, and the main point is this: if sigma 1 2 is 0, I'm going to be back at mu1 here and sigma 1 1. And so I recover the marginal distribution. So it means that y1 and y2 are independent. If it's not 0, then in general, the conditional mean depends on y2, which means that they're not independent. So if I condition on one variable and the distribution of the other part changes, it means they're not independent. And so the only way that these two components would be dependent is if this is non-zero. If non-zero, then as I change y2, this is going to change the mean. Okay. Sounds good? Sort of. There's another point here which I'm not making. This is like a population level regression. So you can, if you look at this enough, maybe you will see later. This very much resembles what you do in regression when you try to regress like a random value, like y onto x. This is very much like regressing y1 onto y2. So this is sort of the best explanation of y1 in terms of y2, and this coefficient is very meaningful. So this is sort of, I'm going to make a comment here. We'll not see this a lot, but population level regression. So if you had infinite sample size, you could observe the infinite, like the distribution that's like, what happens if I regress this? And that this is like the best explanation of y1 given y2 is this. So if I want to explain y1 by just a single vector, if I observe y2, I just output the mean. And this is sort of the nature of regression. And the variance or the covariance thinking is going to go down. This negative sign. It's not obvious, but if you do it for univariate random variable, this part is going to be non-negative, so you reduce the variance. So if you imagine everything is univariate, there is a reduction in variance by condition in general, unless they're independent, in which case this reduction is going to yeah, okay, I may, so usually we don't use this, except the fact that sigma 1 implies independence. That's the main reason why I mentioned this, but there's a lot of use to this. There's a lot of intuition, like you can build from this, and I may sort of sign problems, I don't know, depending how like interested you are in conditioning. But conditioning is one of the major tools in probability, like in statistics. So conditioning sort of just basically allows you to like see how much information or how much uncertainty transforms under assumptions that you make. So if you observe this part, if I observe that, how much sort of more I know. Usually when you know more, you can reduce the uncertainty, you can also change your estimate. So originally we estimated our original guess for y1 was around 0. But if there is a lot of correlation, sigma 1 2 is sometimes called cross covariance. Okay, so this measures how dependent they are. So if this is 0, this would be block diagonal. And the two components are going to be independent, as we showed. If it's not, then there is like a transfer of information. And so what would you get is that this is now your best guess. So once you observe y2, your best guess of y1 is not 0, but around here. So include y2 and also like this transformation that just rescales back things in terms of covariances, which is non-intuitive, but that's the best way to translate from y2 to y1. Sounds good? Sort of. Okay. Yeah, so this is a little bit technical, but there you have it. So sigma 1 2 being 0. So this is the final sort of punchline, basically. In general, if two random variables are independent, they're uncorrelated. So this is true in general, for a general distribution. Independence, dependence implies uncorrelatedness. You remember for two random variables, if they're independent, then this would be equal to that, and this means they're uncorrelated. So independence implies this factorization of the expectation. This implies uncorrelated. Uncorrelatedness means the covariance is 0. Correlatedness does not imply in general independence. This is the point that I want to make. So for a general joint distribution, so if the x and y satisfy a joint distribution, general distribution, have a general distribution, if they're uncorrelated, they're not necessarily independent. But in the Gaussian family, we have that this holds. So, but this implication also holds in the MVM family. So for Gaussian distributions, if you have a Gaussian family, if the two components are uncorrelated, then they're going to be independent. Why? Because of this result that I mentioned. So if the two components, two pieces are uncorrelated, means this part is 0. But once that's part of the covariance. So that's 0, that implies this conditioning just reduces to marginalization. So that argument that I did there just proves that uncorrelated forces this part to 0, and because of the result that we mentioned, uncorrelated implies independence. So in the MVM family, they're equivalent. Being uncorrelated is equivalent to independence. But you have to know that in general, they're not equivalent. So independence is much stronger than uncorrelatedness. Okay, so it implies uncorrelatedness, but not vice versa. Sounds good. You could teach a whole course on multivariate normal distributions, but that's almost done. So these are the properties that I want to emphasize. So multivariate normal distributions under affine transformations don't change, so they're going to be invariant is not a good term, but you're going to stay in the same family if you do affine transformations. If you do marginalization, which is a special case of affine transformations, if you do conditioning, you stay in the same family. If you do part of the vector, conditional part of the vector, the rest is going to be multivariate normal. And that last piece, conditioning, gives you this interesting fact that you have to know that the pieces are multivariate normal. So they have to have a joint Gaussian distribution, these two parts. But once they have they're jointly Gaussian, and these two pieces are uncorrelated, then they have to be independent. So uncorrelatedness implies independence. Sounds good. We'll pause a little bit. Any questions about any of this? Conditioning, marginalization, affine transformation. So these are the important facts about multivariate normal distribution. I wish I had pictures of this. Maybe in a different course, we could do a little bit of pictures in this case to see exactly how this works. Okay, no questions. So last piece is back to the lightening. So if I have y, which is normal, let's say 0, and covariance sigma is positive semi-definite, here's the square root, and we saw in the first slide in the lecture that this would do lightening. So this operation, if I do this, Z will have covariance, which is identity. Now we also know that because this is a linear transformation, right? We will have also a Gaussian distribution. So this means that if I have y, which is normal, which means 0 and covariance sigma, and if I form z to be sigma 1 minus 1/2 y, the mean is going to be 0. The covariance is going to be identity, and also know the distribution is also normal. So this transformation, this whitening, turns a multivariate Gaussian distribution into a very simple distribution. So this distribution you've seen, this is equivalent to the coordinates being independent. So this is equivalent to saying that all the coordinates are IID normal 0, 1. And this follows from the fact that we mentioned. So everything here is 0, so all the coordinates are uncorrelated and they're independent. So this is very useful, in particular, if you invert this transformation. Okay, so if I want to like generate from this multivariate distribution, it's easy to generate from this Z, because I can just generate a random vector. Each individual entry is independently drawn from a univariate Gaussian. I know Z, now I want Y, so I just do the inverse transformation. So from Z to Y, right, anyone knows how to get from Z to Y? So I want to write Y as a function of Z. Z is like this. Yes.
Can you just multiply the E sigma to the negative 1 out, right?
Do this.
And then, yeah.
But then this would be like sigma minus 1/2, sigma minus 1/2 Y. It's going to be sigma minus 1 Y. Yeah, so if you do like the inverse of this, basically, so you want to invert, just invert the matrix, so you get Y is equal to sigma 1/2 Z, right? You can see that this is going to work. So if Z is like this, if I plug this in here, you get sigma 1/2 times sigma negative 1/2, they cancel out. So from Z to Y, it's like that. From Y to Z is like the other one. So these transformations are inverse of each other. So this transformation is very useful for generating. So if you want to generate, let's say in a computer program like R or Python, a multivariate Gaussian distribution, you generate Z like that. Just each coordinate independently is standard normal. And then you calculate the sigma inverse. Sorry, the sigma and then sigma 1/2. So you can calculate sigma 1/2 using the identity calculation. So you know the sigma. You calculate this, you apply it to Z, that would have multivariate Gaussian distribution. Okay, if you want to have, let's say, anyone knows what happens if I want to have, let's say Y tilde, or let's call this, I don't know, X. I want X, which is normal between mu and sigma. How do I get a mu in there as well? If I have Z, can I get from this to that? Suppose I generate Y, then from Y can I generate X? Can you generate, let's say, X from Y, which is just generated from Z? As a function of Y? Yes. Yes, okay, good. If you just add mu,
Sigma will be affected.
great. So it's a constant shift, doesn't affect sigma, it just shifts the mean. This is like a very simple affine transformation. I'm going to stay within the family. I just shift the mean. Okay, so, and this we've seen, like this is just sigma 1/2 Z plus mu. Okay, so I generate Z, I apply sigma 1/2 to Z, and then add up mu. This gives me a general multivariate Gaussian distribution. Okay, so this is the general affine transformation that you can use to map like this canonical multivariate Gaussian to a general multivariate Gaussian. Okay, so affine transformation using this the square root business allows you to do this operation. Okay. Any questions? Okay, we managed to finish early today. I'm going to stop here.